All right, the next section in the TRO textbook is qualitative chemical analysis. Analysis. Yeah. Normally we'd be doing that in the lab. So the Chem 132 lab has a whole last part of the lab on qualitative chemical analysis. And it has to do a lot with our precipitation reaction. So if you're very familiar with your KSP values and what we're about to go into, complex ion equilibrium, you should have no problem with qualitative analysis. It's basically doing our selective precipitation reactions that we did in our last video to separate ions and then confirm them with specific reactions. Since that's going to be covered quite a bit in lab, we won't cover it here. Just note that your book has a whole section on this, so as you're preparing for the qualitative chemical analysis lab, I would read the book starting on page 826 of the new edition of the TRO book. It will really help you when it comes to doing this lab. But let's move on to something that, believe it or not, is also going to help you in the qualitative chemical analysis lab: complex ion equilibria and formation constants. These are equilibrium constants, are called Kf, they're formation constants. It is the constant when a metal ion reacts with a Lewis base. So here we go. For example, silver plus ion aqueous. This really doesn't exist as a silver ion just floating around in water. When you look at silver plus aqueous, it's really a silver with two water molecules attached to it, actually covalently bonded to it. All right, this is called a complex ion because it's silver, which was 1 plus originally. It has our two waters on it. Since waters are neutral, it's still 1 plus. It's a silver with two water molecules on it, still maintaining that plus 1 charge. It is aqueous. It is dissolved in water. This is our complex ion, and our formation constants describe the equilibrium to form these. Note, silver plus is a Lewis acid, has no valence electrons. It has a filled shell. So it acts as all transition metals act as Lewis acids. Water, the oxygen has valence electrons, so it's a Lewis base. And when we have Lewis bases attached to metal atoms, we call those Lewis bases ligands. So we have a silver with two water ligands on it. And the thing about ligands, they are Lewis bases, and they can get kicked off by stronger Lewis bases. All right, so if you have silver with two waters on it, this complex ion, and if you put some ammonia in there, what you find is the two ammonias, which are stronger bases, stronger Lewis bases than water, will kick off the two waters, and the silver will have those two ammonias on it to make a new complex ion and kick off those two waters. Because water is neutral, it's just not very strong. It's not a very strong Lewis base. We often omit it. And so we'll probably write this as Ag plus aqueous because water always gets kicked off by stronger ligands. And so Ag plus aqueous plus 2NH3 aqueous be in equilibrium with our AgNH3 2, our complex ion. And this is our reaction. Note aqueous, aqueous, aqueous. Everything's in solution. So our equilibrium constant is products over reactants to their stoichiometric powers. Since this is the formation of a complex ion, a metal grabbing ligands, this is a formation constant, and it has a value of 1.7 times 10 to the 7th. If you look at table 18.3 in your TRO book, you'll see that these formation constants tend to be quite large. It turns out transition metals really like to have Lewis-based ligands around them. So these formations happen, and these formation constants tend to be quite big. All right, so then here's a question for you. What would happen if you put AgCl solid silver chloride into aqueous ammonia? Instead of just plain water, what if it's aqueous ammonia? Now we know that silver chloride is not very soluble in water. The KSP is like 1.77 times 10 to the minus 10. So what will happen if instead of water, our solid silver chloride goes into ammonia? Well, we know that silver chloride solid dissolves in water to Ag plus Cl minus with a very small KSP. This reaction lies way, way, way to the left. But we also have found out that the silver ion that would get produced here reacts with ammonia with a fairly decent formation constant, 1.7 times 10 to the 7th. So if we add these two equations up, we note that silver cancels out, so AgCl solid plus aqueous ammonia goes to our complex silver ammonium ion and chloride, and you just multiply these two together and you get the equilibrium constant is 3 times 10 to the minus third. So what this means is if you put solid silver chloride into aqueous ammonia, you will get a lot more of it dissolving than if you just put solid silver chloride into water. So solid silver chloride is much more soluble in ammonia than it is in water. And another interesting process with these complex ion formation happens with amphoteric metal hydroxides. Amphoteric are compounds that can act as Lewis acids or Lewis bases. So let's look at AlOH3, aluminum hydroxide. It's a solid, it's not all that soluble. But if we add H+, if we add acid to it, note hydroxide's a base, we add an acid, we will get 3 waters and Al3 plus aqueous. So you can have this solid here of aluminum hydroxide by adding protons to it, you make Al3 plus and water. So AlOH3 will act as a base. Note that AlOH3 solid, if you added some more hydroxide, actually you can put another hydroxide on with this aluminum to make AlOH4 minus. This is a complex ion, and this actually has a fairly decent formation constant, a fairly large value. So this reaction happens quite readily. What this means is if you had aluminum ions in solution, if you add a little bit of hydroxide, just add some hydroxide, add a little more hydroxide, you're going to start forming the solid AlOH3 that is not soluble in water. But if you keep on adding hydroxide to it, all the aluminum will get used up as an AlOH3 solid, but if you keep on adding hydroxide, that aluminum hydroxide will dissolve to form this aluminum hydroxide complex anion here. And now that is water soluble. So what happens with aluminum, one test for aluminum in a solution, is you start adding hydroxide little by little, and if a precipitate forms, and then if you keep adding hydroxide, that precipitate goes away, that's an indication that you have aluminum in solution. All right, that is it for this chapter. We will go on to thermochemistry next.